No stream starting.เร็วสิตาย yes sir and this one in video or even video but I got live of YouTube. Yes. And I don't understand why today we start with 12:40, right? Okay. Yeah. So to right first time in yes let's go redirect to yes and connect that open these right and this one here right and yes Viscosity and let's get into in zurück teilnehmen bleiben verstanden yes yes Patanin in yes Nondagon so to learn Nondagon Patrigon is there alright and yes we start this alright yes okay good morning everybody welcome due to SCI33206, and we will start our lecture today with the first topic. First problem in. Oh no, I didn't turn on the microphone here, right? Okay, we will continue our story in the first problem in the this one, right? I hope that you can hear me well, right? Yeah. ไม่รู้ว่าได้ยินกันหรือเปล่านะครับเดี๋ยวขอเทสเสียงนิดนึงครับthe sound doesn't come right and yeah, the internet is fine and hello, yes sir. Yeah, that's the. I hope the audio doesn't work with this one. Okay. We will consider the pressure difference and we calculate the. We are gonna see what's going on in the relation between between the pressure difference and the surface tension. I don't know whether I can hear you well or not, but let's keep the audio from this one. Okay. Yes. Yeah, the sound is going well. Mercury has an unusually large surface tension. That's the a quite prominent example. Mercury about 465. It's quite large compared to the other in ถ้ามีอะไรด่วนนะครับโปรดพิมพ์มาที่ไลน์ได้เลยนะครับโอเคไหมเพราะว่าตอนนี้ตอนก่อนเริ่มนะครับผมก็เช็คลำโพงแล้วที่หูฟังน่าจะใช้ได้ปรากฏว่าใช้ไม่ได้ครับโอเค no problem. Yeah, we will continue our this one, right? Calculate the excess pressure inside the drop of mercury. Okay, it's a drop of liquid, right? Which is a kind of fluid. So the excess pressure, it means it's delta P, right? Delta P means the excess pressure. Yeah, they asked us about excess pressure, which is delta P, and it's equal to P inside minus P ATM, right? Yeah, it's equal to, according to equation 30, it's 2 gamma divided by R, right? 2 gamma divided by R. This is the liquid drop, and for the bubble we have to use this one, right? The expression that we are going to use, or the formula we are going to use, is delta P 2 gamma by R, right? And what we need to find is the following: the right, the radius is 1/2 of diameter, and which is in this case 4 millimeter. 1/2 of 4, right? It's equal to 2 millimeter, and yeah, in terms of meter, it's 2 times 10 raised to negative 3 meter. And what else? The next one, sorry, this is capital R, so that we would not get confused with the gamma expression, right? Gamma is what they have provided, which is 465, right? Gamma is 465, and that's in the unit dyne per centimeter, right? And we have to convert it to the SI scale, right? Because we will compute everything in terms of SI unit. Yeah, it's going to be 465 times 10 raised to negative 3, right? According to our relation that we have seen earlier here, right? One die per centimeter is equal to 1/1000, right? 0.001 Newton per meter. That's the SI scale. Okay, let's continue our story here. It's Newton per meter, right? Okay, yeah. Now it's time to substitute everything into this one, right? Into the main formula, and 2 gamma means 465 times 10 raised to negative 3, right? And we divide it by the radius, right, which is 2 times times 10 raised to negative 3 again, right? And yeah, you can see that 2 and 2 can cancel, and also here this pair 10 raised to negative 3, and it's equal to 465 Newton per, as you know, it's Newton per meter for gamma, right? But gamma is again divided by a distance in meter, right? So this one is going to be square meter, right? So that's it for the basic formula in liquid drop, and pressure excess means the pressure difference. Okay, so now let's go ahead with the more realistic effect of surface tension. Okay, surface tension is going to be considered quite long later on. All right. Yeah. What's next? There are 2 types of surface tension that will act together with other stuff, other object, right? For example, if we have a capillary tube, which is a kind of experimental tube in the laboratory, we have 2 examples of fluid. The first one is water on the left, and another one is mercury. I'm sorry, the resolution of the figure is not so good. And you can see here that the shape of the liquid inside the capillary tube is gonna be like this. It has the shape like this, okay? And this one is like this, is convex and concave, right? And okay, in order to explain what happens in nature, we will consider 2 forces, 2 kinds of force. The first one is the adhesive force, and the second one is the cohesive force. Okay, if we get into the deep or the zoom of the molecule in between here, between the wall of this tube and the water is composed of H2O, right? The red one is H atom and the white ones, two whites here, are the oxygen atoms, right? And the red one and the gray one represent the glass molecule or glass atoms. Okay. Yeah, you can see that the adhesive force means the force between glass and H2O, the water. Okay, we call it adhesive force. Okay, and there are different positions of force, so there are several adhesive forces. And between among water molecules H2O, there is attractive force inside, and it's called cohesive force. Okay, and in this scenario, the adhesive force, okay, the attractive force between glass and water is greater than the cohesive force, the attractive force among several H2O molecules. Okay, so because this force is stronger than the force among water, so it's tried to bring the water around the capillary tube up. Okay, and that's the reason. Okay, let's move to the right one. Another example, which happens in the opposite way. It's mercury, right? ภาษาประหลอดเนาะ inside the capillary tube, and of course, if you take a look at the zoom or the detail between along here at the wall of this capillary tube, you will see several molecules of mercury, and here is the molecules of the glass again. Okay, the same kind of glass, but on the right side. And again, there will be coercive force, the attractive force among several mercury molecules, and the adhesive force, which is the cohesive force is the attractive force between mercury and glass. Okay, and adhesive force is the cohesive force is the attractive force among several molecules of mercury, and adhesive force is the attractive force between mercury and the glass. Okay, and what we can see here is that the attractive force among several molecules of the mercury is stronger than the adhesive force, the attractive force between mercury and the glass. Okay, because the mercury has a dense molecule, so its attractive force or its cohesive force is very strong, and with this type molecule, they have high cohesive force. Okay, they try to stay together. Okay, they don't want to be attached to the glass at all. Okay, it's quite different to the water. Okay, in water case, we have more adhesive force than the cohesive force. Okay, the atom of the water doesn't the molecules in the water don't attract each other so strongly, so that's why they gonna be attached to the glass. Okay, and that's why we can see this shape. If the figure is not clear enough, let's go ahead to the next one. Okay, here is the clearer form of the effect of adhesive force and cohesive force, right? In the water case, the adhesive force, okay, the attractive force between water and glass is stronger, so that's why they try to bring the water close to the glass up. Okay, and in this case, the cohesive force, okay, the attractive force among several molecules of mercury is stronger, so they try to stay together. Okay, they don't want to be attached to the glass. Okay, and the adhesive force between glass and mercury is lower than, is lighter than the cohesive force among solar molecules of the mercury. So that's why we see this effect. Okay, and one more thing that is quite important is that the scientists or the physicists have found or analyzed the angle of this almost straight line of the water with respect to the plane of the glass here, the capillary tube, and this one, okay, the angle between the glass to the surface of the mercury, okay, it's called angle phi. Okay, you can see that this angle is less than 90 degree, right? And this one is greater than 90 degrees. All right, and yeah, let's go ahead. The gas liquid interface and solid surface, right? Yeah, in the mercury we have a concave. Here we have a concave interface, and here is convex, right? Yeah, it's different. Okay, and one more important thing, if you compare the height of the water level inside the capillary tube and the mercury level, compare it to the mercury surface, okay, it's also different. Okay, not only the shape of the surface of water and mercury are different, but also the height, how they align inside capillary tube when the capillary is laid down inside a big bowl, a big container of those two liquids. Okay, water climbs up a glass tube because the glass attacks it. Okay, because as I told you earlier, the adhesive force, okay, the attractive force between water and the glass is stronger than the cohesive force among several molecules of the H2O or of the water. So because of the strong adhesive force or the attractive force between water and glass is very strong, they try to bring the water inside the capillary tube up. Okay, but in this case your tube should have a small radius. Okay, the tube should not be big. Okay, and that's the case for us. And in the opposite way, we consider the opposite case on the right side, right? It's mercury, right? Mercury behave in the different way. Okay, mercury doesn't have higher level of its surface compared to the mercury surface in the big container. Okay, this is the big container, and if we have a tiny pipe or capillary tube, if we lay lower like this, and you can see that the level of the mercury is lower than the typical surface or level of the mercury in the bowl, in the big container. What is the reason why? And is this true? I would say we have to go to the laboratory or experimental room, okay, in your school. I'm not sure whether you have that hours for the experiment or not. But anyway, what you can observe is the following. Okay, in the mercury case, the level inside the capillary tube is going to be lower than the surface in the big container. Mercury is put down by a glass tube because the glass doesn't attract it. Okay, because as we have seen before, right, the cohesive force among several molecules of mercury is stronger than the adhesive force, the attractive force between mercury and the glass. So because the force inside this liquid is very strong, they try to attack them together, so they don't care the attractive force to other material, right, to the glass in this case. So that's why they have lower level. Okay, unlike this one has more adhesive force. Okay, the attractive force between different materials, okay, between water and the glass. So the adhesive force is stronger than the cohesive force. So the adhesive force brings the water up compared to the water level in the big container. Okay, that's the effects in nature, and I hope you would completely understand the reason behind that we get that phenomenon. Okay, in water case, because the adhesive force is stronger than the cohesive force in the water molecule, right? So there is a rising height here for the water compared to the typical water level. Okay, and of course there are two. We have had before the angle phi, right? Because of this shape of water inside the capillary tube, we have the angle phi, which is less than 90 degrees. And let's say we use this one as the height of the water level. Okay, we don't use the mean value. We use we don't use the highest level. We use the lowest level of the water as the height. Okay, compared to the water level or water surface here. And let's say this is a typical cylinder tube, and it would have the radius, and that radius is called the variable r. Okay, the surface tension is the force F, right? That's what we have seen before in the last lecture. And yes, in the mercury case, okay, the mercury is gonna be the mercury level is gonna be lower than the typical level in the big container. And of course, if we measure the angle in this way, we're gonna call it angle phi, right? And there is the height, right? The height, when we measure it from the typical level of the mercury to the highest level of the mercury here, okay, inside the capillary tube. Okay, here, when the cohesive forces between molecules of a liquid exceed adhesive force, the level of that liquid in the capillary tube is below the surface of the surrounding fluid. Okay, and what about this? Liquid rises in a narrow tube. Okay, please note that we have to consider the narrow tube, okay, due to the result of surface tension and adhesive force. Okay, the reason why we have high height here, because the reason why we have the height here is that we have two quantities. The first one is surface tension, okay, and the second one is the adhesive force, okay, the attractive force between two types of substance or material. Okay, the height that you can find, the height that you can 605. Okay. Oh no, this is heat and gas. I'm stupid. Yeah, this one. The height that you can see in this figure can be expressed in mathematical way like this. Okay, H, whether it's water case or mercury case, okay, we would have the same formula to that. H is to gamma. Okay, gamma is the surface tension. You need to know what type of that liquid is, right? And rho is the density, right? It's kilogram per cubic meter, right? Meter with the power of 3, right? And that's the first thing the first quantity that you may have heard before, right? The density. Yeah, the next one is the gravitational acceleration on Earth, right? Which is 9.8 or number 10 as you want. Okay, up to you what type of thing you want to use. I'm not sure whether I accept all of you in the Zoom or not. Okay, and yeah, so that I can see someone is in the cloud. ลืมอัดด้วยนะครับหมายก่อน okay. Yeah, yes, the formula, right? This one, and R is the radius. R is the radius here from this figure, and phi is the angle here in this scenario, phi, right? And this one is the angle phi right here. All right, yeah, that's what that's the theory we have seen regarding the adhesive force and the surface tension, right? Okay, assume the contact angle between the water and the material. So they consider the water, right? Our material is, our substance is water, so it should be this case. Okay, the level of liquid inside the capillary tube is higher than the level of the liquid in the big container. Okay, and the material of the tube is small enough. Okay, when we look at this figure, they say the angle here is very small. Okay, close to 0. So it means in this case that phi tends to 0, right? Would reach 0. All right, and yeah, when phi is 0, this term is gonna be 1, right? Cosine phi tends to number 1, right? So we don't need to take care of this term at all. Find the height to which water would rise in a capillary tube with radius equal to 5 times 10 is negative 5 meter. Okay. So this is what is that? It is R to rest, right? R in this figure, right? Which is measured from the center of the capillary tube to the wall of the capillary tube. All right, this is R. We know R, we know G, and rho, right? Rho is density of the water. Gamma is what we still don't know, but we can find it from the table, right? The water surface tension, right? At the room temperature, let's say it's 0.073. All right, now it's time to solve this problem. We're gonna use the formula right there, right? H equals before we go ahead with that, we should express everything. Okay, phi equals 0, and gamma is what we can see here, right? Water at room temperature is 0.0073 Newton per meter, right? It's gamma, okay. I'm sorry for that. Maybe it looks like the variable. It's gamma. All right. And rho is the density of the water. Rho water is 1,000, right? 1,000 kilogram per cubic meter.โอเคถ้าคุณตักน้ำมา1ลูกบาศก์เมตรครับมันจะต้องหนัก1ตันนะครับโอเค and g is the acceleration on earth, right? G is the acceleration on earth, which is 9.8 meter per second square, and radius is, what is that? Radius is what they have provided there, right? Which is 5 times 10 to the negative 5 meter. So they want to know the height h, right? So what is h in this case? So we have to apply, we have to use this formula, h, this one, right? H, we're gonna use this formula, right? To gamma and rho g r cosine of phi, right? Yes sir. Here 2 times gamma, which is 5 times, oh no, this is radius, I'm stupid. Gamma is very tiny. Okay, it's only 0.0373 and divided by rho, which is 1,000, and it's 9.8 for the acceleration on earth, and the radius is very tiny. Oh, it's right, it's 5 times 10 to the negative 3, right? Oh, negative 5 even, understand that. All right, that's the thing we have to compute. If you put it into the calculator, all right, you would get 0.298. Okay, and the unit for the is height is meter, right? And that's it for this problem. So let's make the interpretation of this amount of number of quantity. It's, what is that in centimeter? It's 29, almost 1 foot, right? Almost 1 foot, 30 centimeter is approximately 1 foot, right? So this one is 29.8 centimeter, right? So that's the height that you can observe from this one. Okay, the height here is almost 30 centimeter. Okay, yeah, we would go ahead with the next topic, right? We would go further to the next story. All right, yeah, now we are gonna move to viscosity. Okay, as the title said, surface tension and viscosity, right? Now we reach the second term. Okay, viscosity, the extent to which fluids, okay, let's talk about what is the meaning of viscosity. The extent to which fluids yield to shearing force and hence flow easily and quickly depends on a quantity called the viscosity. Okay, when the water stay together, there will be several layers, and the friction between different layers will cause the difficulty for them to move, and that's called viscosity. Okay, viscosity. The first case is that we take a look at the water and honey, yeah, if you try to pour the water from the glass or a cup like this, you would see that it's quite easy to pour the water into the big jar or container like this, right? And on the other hand, if you try the same experiment in pouring by using the honey, so you can see that it's quite difficult to let the honey get into the jar. Okay, when you try to pour it, you have to wait quite long, okay, so that you can see what is going on with that. All right. In a general sense, viscosity refers to the internal friction of a fluid. Okay, you can see that how could we have several layers? They have different layers. Even it's quite clear here. Okay, an ideal fluid is a fluid that is incompressible. Let's say the volume is not doesn't change. Okay? The volume of that fluid doesn't change. Is incompressible, has a constant density because the mass is the same when the volume is the same. Okay, rho is m by v, right? When they say incompressible, it means v is fixed. Okay, v doesn't change. The volume doesn't change with any pressure. Okay, when v doesn't change and the mass of that object stay the same, remains the same, the density is gonna be the same. Okay, let's say rho stay constant and has no internal friction or viscosity, and that's the ideal fluid. Okay, I don't think that we would have ideal fluid that has zero friction in movement at all. I don't think so, but that's the ideal. Okay, the ideal case. Now let's get into the detail of viscosity. We have a pipe like this, and this is a part of pipe or a big tube. Okay, non-viscous flow velocity profile. It means the velocity here at different location across this surface, this area, will be the same. Okay. There is no friction between the pipe and the water or the fluid at all. So this one has a good velocity. This one that has no friction between different layers of liquid. So it has a good velocity. Okay, all layers have the same amount of velocity. So we have the flat profile. Okay, the same amount of velocity at different point of in this cross-sectional area of the pipe of this movement. Okay, but I would say this doesn't happen in nature. Okay, it's the ideal case. But anyway, the theory would say something about ideal first, and we are gonna get into the detail of something more complicated. The particles in an ideal fluid move through the pipe with the same velocity. You can see here the velocity profile. The amount of velocity is the same at different point across this surface or this area. In reality, there is a friction. Okay, as you know, there is a friction. First, there is a friction between the liquid and the solid material here. Okay, the solid material here, there will be friction between fluid and that solid, and that will cause the obstruction, and the fluid close to the surface inside the pipe is gonna have lower velocity, and here in the middle of liquid, okay, because it has only the friction between nearby layer of water or of that fluid, so the friction is not high. When the obstruction is not strong, okay, the water or the fluid in this position, is gonna move very easily, so its speed or velocity is gonna be high at the center. Okay, and when you are close to the center, you will have less friction, and your velocity is gonna be increasing and increasing. All right, and yeah, the velocity of the fluid particles is zero at the surface. Okay, we would say it has zero movement. Okay, no movement, or because the friction is very large at the surface of the pipe, and increases to the maximum value at the center of the pipe. All right, and what else? Let's get into the formula, right? This structure, a layer of liquid between two solid surfaces in which the lower surface is fixed and the upper surface move to the right with the velocity v. So assume that we have a very sticky fluid, right? And we try to attach this part of liquid to the surface AD, and before that you are at BC, right? The liquid just stay upright, and when you pull this bar, this flat plane, okay, this you try to pull this plane to the right. Okay, the liquid on the lower bar here, lower plane here, doesn't move, but this one is gonna move because it is attached to this plane, right? And it's gonna move to the right as same as the plane. And what they have found is that you have zero velocity at this location because it doesn't move, right? And you have a very high velocity at this location, right? Because that the highest amount of movement in this location. All right, and this is the distance d, and the distance that this moving fluid moves is delta x. Okay, and delta x is velocity times delta t, right? Because as you have learned from your material 4, right, v is delta x by delta t, right? And when you move delta t to the left hand side, you are gonna have delta x, which is the distance here, okay, the displacement from the first stage to the second stage. All right, and in figure 25, a portion of liquid is distorted. Okay, this is distorted from its original shape A, B, C, D. Before that, you have the shape of liquid like this, right? This one. But when that one moves, okay, it's gonna bend it like this, okay, in to the shape A, F, E, D. A, E, F, D, right? This one. A, F, A, E, F, D, okay, the blue one, from the green one to this one, okay. And yeah, a moment later, and the force required to move the upper plate and distort the liquid is proportional to both. Okay, let's realize that, okay, if you have bigger area, okay, between the fluid to the plate, right, you would see that you are more difficult to move this one, right? And it depends on also the speed, okay. If you want to move it quickly, you need to have more force, right? And what else? Further, the force is inversely proportional to the distance d between the two plates. If these two plates are quite close to each other and you have the same type of fluid, you will find that it's quite difficult to move this plate, right? So if you go If you let the distance be smaller, you have to have more force. Okay, you have to exert more force to this plate. Yeah, it does mean that if you have greater distance, you need more force. No, it's not the case. If you have less distance between two plates, you need to have more force. Okay, and the force is A can be expressed as like this, right? A times velocity, okay, divided by D, and eta. Eta is the coefficient of viscosity of the fluid, and the coefficient of viscosity of solid fluids is shown in this table. Okay, please don't be confused. Okay, the fluid had different properties. Before that, we have seen surface tension, right, which is Newton per meter, and it depends also on the temperature. If you have higher temperature, the surface tension is going to be lower too, right? And the same here. If you have water at 20 degrees, you would have 10 times 1 times 10 is negative 3, okay, 1 by 1000. And if you increase or you make the water hot, like 100 degrees Celsius, you would have 0.3 times 10 is negative 3, okay. You can see this 0.3 is less than 1.0, okay. When you increase the temperature in both quantities, okay, you increase the temperature of water from 20 to 100, you would have less surface tension too. And do you know the reason behind it? What reason behind it? Why we have less amount of viscosity and surface tension? ทำไมเราถึงมีค่าความหนืดต่ำลงเมื่ออุณหภูมิของเหลวนั้นสูงขึ้นครับมีใครตอบได้ไหม Any idea to that? Just type it in. If you wanna leave the answer to me, just type it. Okay. ช่วยพิมพ์ตอบมาหน่อยว่าทำไมมันเวลาเราเพิ่มอุณหภูมิแล้วมันมีค่าพวกนี้ต่ำทำไม viscosity ต่ำแล้วก็ surface tension ต่ำครับระหว่างที่ผมรอคำตอบคุณขออนุญาต capture หน้าจอเพื่อส่งนะครับ Any idea to that มีใครตอบได้ไหมเอ่ยWhat is the reason why we have that oh no. Yeah, you may guess that when we insert the heat into any molecule, the bonding force or the attractive force among several molecules is going to be destroyed, right? So they will have less attractive force, and once they have less attractive force, it means they can move easily, okay. When they move easily, it means its viscosity is not high, or it's not high or it's lower, right? I hope that you would understand this situation. Okay, let me into 92, right? Oh no, SCI. Alright. Yeah. For something else, for other materials, glycerin, whole blood. This is quite close to our life, right? It's the whole blood, and yeah. Whole blood has at the typical body temperature, right, 37 2.7 times 10 to the negative 3. Okay, you can see that the blood has higher viscosity than the water, right? So yeah, if your blood cannot flow well, your body is gonna get cold. Okay, because the one of the functionality of the blood is to keep your body warm, right? Yeah, if your blood cannot flow well because of the viscosity, you may get sick because the temperature of your body is already too low. All right, the next thing is glycerin, right, which is the kind of fluid that you may have seen at the room temperature. Is very sticky. It's 1500, okay, times 10 to the negative 3. It's 1.5. Let's talk about the unit of the viscosity, eta, right? You can see here on the left hand side, this one is Newton, and it's meter square, right? And sorry, it's meter per second and divided by meter, right? So here is the unit of eta, right? Unit of eta. So what is the unit of eta? If you first, you can cancel the meter and meter, right? So you would have meters square by second at this side. You move second to the left, you move meter square to the left. At the denominator, you would have Newton second per meter square. Okay, and that's the unit of viscosity. 12:40 ผมต้องเลิกกี่โมงนะงงลืมไปแล้วครับ 14:20, right? 14, you have to leave. You have to leave this class. All right. Yeah. And the last one is 10WT motor oil. Okay. If you have ever noticed the oil that is used to lubricate several components or parts inside the engine, has to have some amount of viscosity. Okay, because when they have a large amount of viscosity, the component, the metal or any kind of metal, would have a thin film of that stuff, and with this, with that stuff is the friction is going to be reduced. Okay, so that we can have the long age of the engine. Okay, long life of the engine. Okay, and axle of a few centimeter. Let's start with this example. An axle of few centimeters diameter rotates in the bearing with like this. Oh my god, what is that? This is the axle, and we have here in the orange ring here, it's oil. Okay, this is the cross-sectional view of that bearing rotation. Okay, this is the axis. Okay, and it's the axle, and this one is like a big wheel. Okay, if we rotate it, it's gonna move. Okay, and yeah, assume that the gap, which is the depth of the yellow area here, is 1 millimeter. It's filled with SAE. SAE is a Society of American Automotive Engineering or something like that. Okay, that deal with automotive engineering in United States. Okay, 30. This is the code of the viscosity controlled by this society. Okay, this is the American Automotive Engineering Society. They have provide the value of viscosity. They say SAE30 oil. Okay, and it has, okay, doesn't matter if you don't understand it. Eta is viscosity, what we have just learned, right? Newton second per square meter. It's 200 meter Pascal per second. So if you substitute the unit of Newton, you're gonna have this one, okay, millipascal and second, and a linear speed of 1 meter per second. So this object is moving with velocity 1 meter per second. Okay, it moves with the speed of 1 meter per second. Yeah, like that. Then we arrive at the question: if the total cylinder area is 100 square centimeter, right? So the area inside this bearing, okay, is 100 centimeter. Okay, neglect the depth difference, and determine the force needed to overcome the viscous friction. All right. So what they have provided is A here, right, which is 100 times 10 to the negative 4, right, and it's in the SI system, meter square, and eta is what they have provided there. D is 1 millimeter, or in the SI system is gonna be negative 3 meter, right? The unit here is already the same as what we have learned, what we have seen. Yeah, you don't need to take care of that. Okay, this is 10 WT, but this one is 30. So its viscosity is greater than that. It's approximately the same. Okay, 30 and 10. Okay, yeah. Now it's time to compute. Oh my god, no, it's milli. This one is milli, is not meter. So we have to multiply it by 10 with the power of negative 3, right? 10 less than 2. 10 less is 2 negative 3. So because it's milli, Pascal per second is Pascal times second correspond to this one, right? Because Pascal is Newton per meter square, right? Pascal is something like that. Pascal is equal to that unit, right? Newton per square meter. So we have here Pascal times second, and M is the milli. Okay, this is milli, which is Taylor's negative 3, right? So we start to solve this problem, and yeah, the formula is F equal A times V and divided by D and eta, right? Eta, and what you can see here is that A is 100, or it's, sorry for that, it's 10 less negative 2 square meter only, right? And what else? Velocity is, the speed is 1 meter per second. Okay, simply number 1. And the next thing is eta, right? Eta is what they have provided, which is 200 millipascal second. So it's 200 times 10 less negative 3, and the unit in standard form of viscosity is Newton second per square meter, right? And the last one is the distance D, the gap, right? The gap in the yellow area here, and you could see that D is 1 millimeter, or in SI system 10⁻³ meter, right? So let's substitute everything into this formula, into this one, right? A V by D times eta. F will be A, which is 10⁻². V is velocity number 1, and eta is 200 times 10⁻³, right? It's 0.2 actually, and divided by D, right, which is only 10⁻³. So you can cancel this one and this one, right? And if you divide it, this one by 100, it's gonna be number 2, right? So the force would remain only 2, and the SI unit for the force is Newton, right? So, and that's it for our problem related to viscosity. It's 2 Newton right here. Okay, the answer. Now let's move to the next topic, which is fluid velocity. Okay, fluid velocity is greatest in the middle of the pipe, and here is the velocity profile of a fluid flowing through a uniform pipe of circular cross section. And now we would be close to the fluid equation, right? In figure 28, this one, okay, in this figure, a section of a tube of length L, okay, the length here is L, and it has radius R, okay, radius measured from the center of the pipe to one side of the wall inside the pipe is R, denoted by the capital R, containing a fluid under pressure P1. Okay, here we have P1 and a pressure P2 on the right. Okay, at the right side we have P2, on the left side we have P1. Okay, this is measurement of R. And the rate of flow unit, volume per unit time, the rate of flow depends on the pressure difference P1 and P2. Okay, we're gonna consider the flow rate. Okay, how much fluid would flow per time, and how much fluid would be seen or measured in terms of volume. So the dimension of the tube, okay, is another factor that the rate of flow depends. Okay, if the pipe is large, okay, the fluid would flow very well. Okay, you may have observed that if you are in your villa, in the place where you live, if they have provided a bigger pipe of water, you would have better flow of water, and that's also the reason why the rate of flow depends on the dimension of the tube. And it's also depend on the type of liquids. Okay, if you want to transmit crystalline to your house by using the water system, it's going to be difficult to transfer the crystalline because the crystalline has high viscosity. And with all of this, okay, the rate of flow would depends on the cross-sectional area, the size, the dimension of the tube, and the pressure difference, and the length of the pipe too. Okay, if you have longer pipe, you would not get better flow of water. Okay, so the relation known as Poisson. Okay, his name is a French name. Okay, and is given by, I'm not sure how could we pronounce it. สอนมาปีที่แล้วก็ต้องมานั่งฟัง Yeah. Pronounce. How to pronounce. Pronunciation. Okay, here. Okay, now let's hear the correct way to pronounce these words. It's a French name. Okay, now let's start with that. Oh no, this is the advertisement from the Food Panda. You know, bonjour means good day. Bonjour. Okay, you may have ever heard bonjour. Okay, if you are not clear, you may try to ask this guy again. Okay. Bonjour. Okay. So yeah, I'm sorry for that. I didn't visited France before, and I have zero knowledge about French. Okay, I have never studied French at all. Bonjour. Okay, it's the equation by Bonjour, and as that guy said, he is a French physicist. Okay, he's quite famous in formulating the relation of the water of the liquid flow, and his relation, the formula that he discovered is this one. Okay, delta V by delta T is pi r ธนานัทนี่มาใหม่หรือเปล่าธนานัทpi r with the power of 4. Okay, ธนานัท is already it. Anyone else มีใครมาใหม่ไหมครับที่ผมไม่ได้ capture ธนานัทพิมพ์ทั้งสองที่นะ alright yeah pi r with the power of 4. Okay, and the pressure difference P1 minus P2 divided by 8 eta L. Alright, 8 and eta L. Yeah. Eta is the viscosity, right? And as they say, it inversely depends on viscosity. If that fluid has a large value of viscosity, it's gonna move difficultly. Okay, so eta appears as the denominator, and L2, right? If we have a longer route of water flow, we would have less fluid rate, right? The left one is known flow rate. Okay, the rate of flow rate. Okay, we call rate because there is a division per time. Okay, and yeah, that's the Boissier. Okay, the French name Boissier's law. A person receives the blood transfusion through, okay, this guy needs to have a new amount of blood, and through a needle. Okay, the needle has the radius of 0.2 millimeter, which is very, very tiny, right? And the length of that needle, okay, the plight connected to the needle is 2 centimeter. Okay, it's, the length of the needle is 2 centimeters, not much. And the density of the blood is greater than the typical water. Okay, 1,000 kilogram, right? Here it is 1,050 kilogram. Okay, it's a little bit heavier than the typical water, the pure water. And the bottle supply the blood is 0.5 meter above the patient's arm. What is the rate of flow through the needle? Okay, let's draw. เวลาทำกันบ้านนะครับโปรดวาดรูปนิดนึงนะวิชาฟิสิกส์มันคำนวณไม่ยากนะครับเอาเรียกว่าอะไรลดความยากของที่ไม่เหมือนแมทเอาแรงตรงนั้นมาวาดรูปให้ผมดูหน่อยนะครับเพราะว่าคุณขึ้นมาโจทย์ตัวหนังสือแล้วคุณก็โซฟเลยผมนึกภาพไม่ออกเลยนะครับคุณวาดรูปให้ผมด้วยนะครับการบ้านนะครับเช่นเดียวกันนะครับข้อสอบนะครับโปรดวาดรูปนะวิชาฟิสิกส์นะครับ Okay, we have a container that keeps the blood here, this one, right? And we connect it through some pipe. Okay, but pipe is not the main consideration. We have here the needle. Okay, needle is a very small thing, right? And it is inserted in human arm. Okay, this guy, this person, all right, this person, and this is needle, right? All right, so the blood, which is the red one here, is gonna flow like this, right? It's gonna flow through the needle and move into the patient body. All right, yeah, let's capture every detail. The radius of the needle here, needle with R equals 0.2 millimeter. All right, yeah, the radius like this is R, 0.2 millimeter. And what else? The length of the needle is 2 centimeter, not so long. Okay, this one to here. Okay, it's 2 centimeter. Two centimeter, 2 cm. All right, and the density of the blood here. All right, the inside the container row of blood is 1,050 kg per cubic meter, right? And the bottle supplied is higher. It's 5. Oh no, not 5 meter. 5 meter is too high. It's 0.5 meter above the needle level, right? It's 0.5, so H is right there. So now we are gonna use this formula, the procedure formula. So what they want to know is rate of flow right through the needle. So the question is delta V by delta T. What is that, right? So we're gonna use the procedure formula, right? And we need to know R, which is the capital one or the not small one. R is already there, and pressure. What is pressure different? P1 minus P2. Okay, P1 is right here. This is P1, and here is P2. Right, pressure at this level. So what do you think? P1 and P2. What is that? Okay, we know the viscosity, right? Viscosity of the blood. Or not? Yeah, we know the viscosity of the blood from this table. Whole blood here at the at the typical body temperature 37 degrees of Celsius. So we have viscosity of the blood is 2.7 times 10 less negative 3 Pascal second, right? Simply speaking, Pascal second, and yes, the eta, and in the Boursier formula we need to know more the length, right? L is the length, which is 2 centimeter or 2 times 10 negative 2 meter, right? That's the length in SI scale, but we still get stuck with P1 and P2, right? Pressure difference. What is that? What is the pressure difference in this scenario? P1 and P2. Of course, you would know that from the physics in a couple of years ago in your school. P1, okay, P1 is greater than P2, of course, right? Otherwise, there will be no flow of blood at all, okay? If P1 is less than P2, the blood is gonna move reversely, okay, in the opposite direction. This one, P1 is greater than P2, and P1 is greater than P2 by this amount, rho g h, okay? Rho is the density of the blood, g is the gravitational acceleration on Earth, and h is the height. All right, so let's go to the Boursier formula. Delta V by delta T, right? It's equal to pi and R with the power of 4. And the pressure difference is rho G H, right? Rho G and H divided by 8 eta L, right? So now let's substitute everything to this one, right? So pi is pi, and R radius is 0.2 millimeter, or simply speaking, 0.2 times 10 negative 3 meter, right? With the power of 4 too, right? And rho is the density, which is 1050 kilogram per cubic meter. G is 9.8, and height is 0.5. Okay, 0.5 above the needle level. And 8 is number 8. Okay, nothing more. Eta is the viscosity that we have looked at before, right? For the blood, which is 2.7. Okay, 2.7 times 10 to the negative 3 Pascal second. And L is the length of the needle in this one, right, is 2 centimeter. It's gonna be 2 times 10 to the negative 2. All right, when you put it into the calculator, you're gonna have the result, and it's equal to it's equal to 0.5 9 and 9, okay, almost 0.6, and it's cubic meter per second. All right, and that's the flow rate of the blood, rate of flow of the blood through the needle here, okay, through the needle. Okay, now the time is over. I have to leave you from this class, right? If you have any question, okay, we will continue next time on Friday about next topic, right? Fluid pressure and buoyant force. Okay, we have completed the Poisson expression, Poisson formula, right? And I have tried to solve this one to you, right? If you have any question, just let me know. If not, we're gonna quit this lecture right now. And I think only chiasid, right, is on leave, nothing more, right? ถ้าใครลาทำอย่างอื่นโปรดแจ้งด้วยนะครับถ้าเท่าที่ผมทราบจากห้อง605ก็คือมีชัยสิทธิ์ลาทำกิจกรรมสวนนะครับก็ now we have to leave, and there is no homework, and please submit the homework as soon as possible. I'm gonna let you know the results. บ๊ายบายครับสวัสดีครับ Next time is 14, 20, 16. AirPlay test. Okay, great. Just look at this. This one. Yes, this one. Still M605. You have to stop this. Okay, it's time for M605, right? Good afternoon, everybody. Welcome you to SCI33206, right? Today, two students are gonna meet, right? Who are okay. The first person is Thanakorn, right? And the second one is Patihan. If anyone else is trying to, what's that? If anyone who would further be on leave, okay. Okay. Yeah. I hope that everybody would be fine, right? I didn't see you. Okay. Anyone else who would like to join the Zoom? Just let me know. มีใครจะจอยอีกไหมครับมีใครไหม Right now there are only two people in the Zoom, okay, which are both me. Okay, first time. Okay, only two people right now on this in the Zoom, right? No one else, right? If not, then we are gonna go ahead immediately, and I hope that you would type your name in any channel, up to you, in YouTube or any kind of thing, right? All right, let's go ahead with our route in solid and fluid. Yeah, welcome you again, M605 to SCI33206, which is physics number 5 on the second semester for you, right? Before you leave the school. จะพยายามดูนะครับถ้าเกิดว่าใครเข้ามาที่ซูมนะก็ถ้าเกิดว่าผมไม่ได้ให้เข้าก็คุณก็โทรทางไลน์เลยก็ได้นะถ้าเกิดต้องการด่วนอะไรอย่างนี้นะครับเพราะว่าบางทีมันดูหลายอย่างนะครับควบคุมหลายอย่างผมก็จะมองไม่เห็นคุณ Okay, let's continue our story. Before that, we arrive at this formula, right? It's the pressure difference, P outside minus P inside minus P outside, right? Outside means the temperature at the surrounding, and inside means the pressure inside that fluid, whether in the bubble form or in the liquid drop form, right? It's the pressure difference in the bubble form is twice greater than the amount in the water drop. Okay, yeah, because of the surface tension, right? And yeah, there are two formulas for gamma and 2 gamma, right? And R is the radius to that whether it's a bubble or the drop. And let's say if the drop is assumed to have the circular shape, okay, we're gonna have that. All right. Okay. Natawin. Okay. Two people. Prasit and Panatatnap. Okay, I'm trying to look at you. Non-Viscous too, right? งงกับนนทกรนะว่าทำไมเข้ามาก่อนนะครับหรือว่าผมนึกว่าผมพลาดเวลาอะไรสักอย่างนนทกรเข้ามาตั้งแต่ช่วง604ผมผิดอะไรหรือเปล่าก็งงตอนนั้นครับ alright โอเคผมก็นึกว่าผมมันถึงเวลาสอนแล้วผมไม่ได้เข้าหรือเปล่าเห็นนนทกรมานี่มัน605เวลา605แล้วเหรอครับทำผมตกใจไปด้วยโอเคnothing right so let's go ahead with that in yeah okay yeah let's remind and the pressure difference right sometimes it's known as pressure excess okay excess mean the additional amount okay of something okay Pritinan has typed his name in the YouTube channel anyone else okay so Supavit นะครับ Supavit okay Supavit just get back from the BMAT right BMAT exam right I hope that the current trend in engineering would be biomedical engineering right yeah I would say it's true because during my PhD generation it's like 10 or 12 years ago biomedical engineering was quite popular at that time and at the moment the most active department in engineering at the university where I'm working is the biomedical engineering okay yeah it's quite modern department I hope you would enjoy that and yeah let's go ahead I may not hear well because there is a problem with the speaker if you say something I may not hear you in the Zoom okay now let's go ahead with this story we arrive at the first example in the application of bubble and fluid drop right Mercury right is chosen as the kind of fluid and yeah ถ้าใครจะเข้าอีกนะครับผมพยายามมองอยู่นะ yeah Mercury has an unusually large surface tension okay if you take a look at the table of surface tension as we have seen last time the mercury is over there right at the room temperature 20 degrees Celsius it has 0.465 right which is 20 times higher and greater than ethyl alcohol or even 15 times higher than water right it has very strong surface tension you can see here right? That's why they say has an unusually large surface tension okay about 465 dyne per centimeter what is dyne per centimeter dyne per centimeter is already addressed or talked before right it was talked before if you want to convert it to the SI scale you're gonna have you need to divide that amount by 1000 or multiply it by 10 raised to negative 3 right then you have the amount in SI scale Newton per meter all right yeah now we arrive at the question calculate the excess pressure inside the drop of the mercury okay we have here the drop of the mercury right okay Hg is chosen as the material right so Hg is mercury right okay and from the table on the left side you can see that the gamma which is surface tension with gamma Hg is equal to 0.4. What happened? 0.465, right? In unit for surface tension is Newton per meter, right? The value they have provided in the table is in the SI scale. So yeah, you have to convert everything in the SI scale. Here is the surface tension, right? Surface tension, right? Yeah. And what's next? Yeah, the question is calculate the excess pressure inside the drop. So we have to draw the drop. So it's like assume that the drop, Mercury drop. Mercury drop has the shape of sphere. Okay, it's spherical. Okay, it's spherical. It has the shape of sphere. It's brown. Okay, that's the ideal case. Okay, and it's fluid drop, right? So there is no air at all. It's drop. So it filled with mercury inside, right? It's not air. So yeah. Based on these, we have to apply this formula. Okay, we cannot use this formula because this is the formula for bubble. Okay, this is the formula for bubble. Here is the formula for the drop. Okay, fluid drop. Okay, it's different in bubble has higher pressure excess or pressure difference inside 2 times. Okay, twice the value of the pressure excess in the drop. So we need to use the equation 30, number 30, and yeah, what they have provided is the radius. Oh no. They say the diameter D is 4. All right. Diameter here D is 4 millimeter. Okay, that's the diameter of this mercury drop, and the surface tension is 465 dyne per centimeter, which is equivalent to 0.465 in SI scale Newton per meter, right? And what else? Yeah, you can see that the radius would be d by 2, right? Half the diameter, and the diameter is 4, so it's going to be 4 by 2, right? Times 10 to the negative 3 in the SI scale in unit of meter. You would have 2 times 10 raised to negative 3 meter. Okay, that's the radius. When our target is this formula, okay, 2 gamma by r. So pressure difference, pressure excess, excess pressure is equal to delta P, okay, which is delta capital P, which is, oh no, I use small one, right? Small p, and it is P outside, no, P inside minus P outside, outside of the drop, right? Outside the drop, or it's equal to P minus P ATM, okay? But we don't get into this relation, okay, because what they want to know is only delta P, right? What they want to know in this example is only delta P. What is that? So we're gonna apply, or we're gonna use the formula number 30. Delta P equals to gamma, right? As a element to gamma by R. To gamma by R. Okay, and yeah, gamma is what we have got before, which is 0.465 by, oh no, sorry, I missed, I forget number two, right? 2 and yeah, divided by R radius, which is 2 times 10 to the negative 3, right? And yeah, you put it into the calculator, you would get you would have the cancellation between number 2 above and lower, and just yeah, we would flip the Taylor's negative 3 to the upper portion to the numerator, and we would end up with 465 only, and it's in the unit of the pressure is Pascal, right? It's Pascal, and or Newton per square meter, it's the same thing, right? Newton per square meter too, right? Yeah, that's it for this problem. I hope it's not difficult. Alright, this is acceptable to you พอได้นะครับไม่ยากเกินไปนะ alright, yeah, now we go ahead with the next topic, right? We still alive at surface tension, but we will consider different setup, okay, in a more complicated setup, okay. But before that, we would okay, you have seen the surface tension from the basic formula. Gamma is F by L, right? In certain scenario, you have pressure difference for gamma by R for the bubble to gamma by R for the liquid drop. Right now, we will consider the experiment when we leave the, you know this one, right? It's a kind of tube, right? Capillary tube. And I don't know whether we would have any chance to get into the laboratory of physics so that we can make some experiments or not, okay? ไม่รู้ว่า โควิดอย่างนี้นะครับคุณจะได้มีโอกาสได้เข้าไปทำแลบอะไรบ้างไหมนะครับก็ถ้าอยากทำก็บอกนะครับโอเคมาอาจารย์ครับผมตื่นเต้นอยากทดลองไม่อยากเรียนแห้งๆแบบนี้อะไรอย่างเงี้ยครับก็เคยถามรุ่นพี่คุณเขาบอกว่ามันต้องจองเวลาเพื่อเข้าไปทำแลบนะครับโอเค in laboratory you can ห้องทดลองเนาะของคุณน้องมาปลายครับwe would have a big container like this. It's like a bowl or something like that, and we have a small pipe like capillary, and the effects is the following. When you leave, okay, water is a kind of fluid, right? And mercury is a kind of fluid in is a type of fluid in yeah, what we could observe is the following. At the end of the capillary tube, you can see the shape of the water inside the capillary tube like this, okay. It's convex, and this one is concave, okay. ก็คือหงายกับคว่ำนะครับ okay. This is the ending point of the mercury inside the capillary tube. In yeah, that's what we could observe from the experiment in laboratory. In what is the reason behind that? Okay, what is the reason behind that? Why do we have this shape? And if you take a look at this area, okay, it's only this part, okay. You could see it's like this. Okay, and the physicists have defined the angle of this plane, okay, with respect to the capillary tube vertical axis. Okay, it's called angle phi. This is the glass, right? The capillary tube is made of glass, and for Mercury, the shape of the surface, Mercury surface is something like this. Okay, and what is the reason why we have different shape of liquid attached to the capillary tube wall? So what is the reason behind that? So in order to see the reason, we have to take a look at the close picture to that. Okay, close picture is the following. You pour the water inside the capillary tube, you see this shape of water, right? This one. And you pour the mercury into the capillary tube, you see this surface of the mercury inside the capillary tube. The reason is the following. Okay, there are two types of force. The first one is called adhesive force. Okay, adhesive force. Adhesive force is the attractive force. Is the attractive force between mercury and between mercury and glass. Okay, that's that's the attractive force between mercury and the glass. And there is another one which is between water or mercury. Okay, it's called this glass too. Right, glass, and this one is Hg or H2O or water. Okay, whether it's mercury or water. Okay, water is on the left and mercury on the right. And there is another type of force which is called cohesive force. That's the force. It's attractive force too, right? It's a kind of attractive force among several molecules of the same substance, or same substance. Whether you have water or mercury, okay, you would have cohesive force. Okay, the attractive force between the water molecules, among several water molecules, and among several mercury molecules. Okay, yeah, you can see that there are two types of force, right? The first one adhesive and cohesive. The second one is cohesive. Why we have this shape for the water inside this capillary? Well, in the water case, the adhesive force, which is the attractive force, okay, this is the glass molecules. Okay, it's composed of silicon and so on, right? And here is the water molecules, right? It's composed of one oxygen, the big red one here, and the two white dots, two white circle represent the oxygen, the hydrogen, smaller atom, right? Hydrogen atoms, and this is a single molecule, right? And yeah, you would have also another molecule of water, H2O, right? One H and two oxygens atom. and between this molecule and this molecule there is an active force. Okay, it is called cohesive force. Okay, cohesive force means the force of the same type of molecule. And between the silicon molecule in the glass and the H2O molecule, the water molecule, there is an active force too, and it is called adhesive force. Okay, different pairs of silicon oxide molecule to the water, there is adhesive force too, right? Adhesive force at different places. Okay, in the water case, the adhesive forces are greater, are stronger than the cohesive force inside the water molecule. So with this stronger force, the glass try to pull the water around or close to the surface inside the glass up. Okay, they try to pull the water close to the wall up, and that's why we have this shape. And once we get to the middle of the capillary tube, it's far from the glass and the attractive force is not strong, right? There is only cohesive force among several molecules of oxygen, of water, right? So there is no adhesive force at all. But the water molecules close to the capillary wall would have more adhesive force, and it's called adhesive force, right? They try to attract the water molecule around here, and they try to raise the level of the water a little bit up. All right, and let's get to the right situation. What happened with the Mercury case? The gray one represents the Mercury molecule, okay, or Mercury atoms, and one piece represents one molecule, and of course, with the same type of matters, there is additive force too. But Mercury is a fluid that has a great amount of density, so they stay quite close to each other, and the additive force is quite strong, and it means the cohesive force for the Mercury to Mercury is very, very strong. Compared to the additive force between the glass and the Mercury, it's called adhesive force here, right? This is the adhesive force between Mercury molecule and the glass molecule, silica or silicon oxide or something like that, is not so strong compared to the cohesive force here. So the Mercury molecule are attached to their group, to their colleagues, to their neighbors, okay, quite well. So there is no strong force to bring them to be close to the glass. So that's why we have this shape for the molecule inside the capillary. So that's the reason in nature, okay, because physics is a kind of science. So the scientists try to give the reason why we have this in nature. All right, yeah. We have the angle phi for water, okay, because the glass try to attract the water close to them, right? So this plane has the direction like this, and there is an angle phi which is typically less than 90 degrees, and we have the angle phi here for the Mercury case too, but the adhesive force between Mercury and glass is not strong, okay? It's not stronger than the cohesive force among several Mercury molecules, so they try to stay together, okay, because their attractive force is stronger. So that's why we have this shape, and at this curve there is the line here, the tangent line, and when we measure the angle from the glass wall vertically, to this line we're gonna have the angle phi, and phi will be usually less than 90 degree โอเคมุมป้านนะครับอันนี้มุมแหลมนะโอเค and yeah the interface the surface of fluid gas and liquid interface is gonna be different. Okay, this one is concave interface and this one is the convex interface. Okay หงายกับคว่ำนะครับโอเคไหม and the water climbs up. Furthermore, apart from different shapes of fluid inside the capillary, if you take a look at the broader view, okay, in the wider view, when you compare the fluid level inside the capillary tube to the surrounding level of the liquid, okay, inside a big container or in the jar or in the bowl or something like that. For the water, you could see that the level of the water inside the capillary tube is higher than the level of the surrounding water inside a big container here. And compared to another case, on the other hand, the mercury level inside the tube, the capillary tube, is a little bit lower than the mercury surface in the big container here. Okay, and what is the reason behind that? The reason behind is as follows. As you know, the water molecule and the glass molecule have the strong adhesive force, right? The attractive force between water molecule and the glass molecule is very, very strong. So they try to pull the water up inside the capillary tube, okay? But please note that you will be able to notice this effect only when you have or you use the small tube, okay? You use a small you use a capillary tube with small radius, okay, you would see this effect. But if you use a very big capillary tube, there will be no difference in level of the water at all inside the capillary tube. Okay, you could see it only in the inside the small or tiny capillary tube. And this one too, what is the reason behind it? Because the attractive force between mercury molecule is stronger than the attractive force between mercury and the glass. Okay, this force is greater than the force between mercury and the glass, so that's why this surface or this level is lower than the typical level of the mercury in the big container. Okay, it comes from the attractive force or the adhesive force, right? The idea of adhesive force. Okay, yeah, whether the adhesive force is greater than the cohesive force. Okay, that's the criteria. That's why we have two cases of experiment results. Okay, now let's get into the basic calculation in this topic. Let's consider the water case, okay, the fluid that has more adhesive force than cohesive force among their molecules, right? In the water case, of course, the water is gonna have rising area here, right, with the height of variable h, okay, and the angle is measured with respect to the capillary wall by angle phi. And let's say this capillary tube has the radius by r, okay, small r, and yeah,ที่605นะจะมีคนชอบลืมพิมพ์ชื่อนะครับโปรดอย่าลืมนะคนพิเศษอะจำชื่อไม่ได้แล้วนะชื่อเลยนะนั่นแหละผมจำไม่ได้นะครับโอเคมาการบ้านก็จะส่งช้าอยู่คนหนึ่งอะครับคุณโปรดอย่าลืมพิมพ์ชื่อนะคนนั้นนะครับมาเปิดเรียนมาวันแรกก็หาที่พิมพ์ชื่อไม่ได้นะครับคนนั้นนะครับผมจำชื่อไม่ได้ละ Okay, and for the Mercury case โอ้นี่ไงพูดถึงก็นี่นะครับเจอแล้วครับพยายามเข้ามาที่สูนะครับเพิ่งมองเห็นนะครับแล้ววิพลนะครับโอเคwhat's that oh what is going on oh คุณครูจอยก็พยายามเข้าโอเคแล้วพี่พลรับผมเข้าด้วยแล้วครับนะครับไม่รู้นะ247 right 27เข้าสายประมาณ30นาทีนะแล้วก็ผมรับเข้าช้าไปประมาณ7นาที alrightโอเคเดี๋ยวครับขอokay the mercury case right yeah the level of mercury inside the capillary tube is lower than the level of the mercury surface in the big container in the bowl or in the cup or something like that right but please note that you will see this effect only when you use a tiny capillary tube okay if you use the big capillary tube you will not be able to observe this effect at all okay that's the two things and the angle here when we measure from the capillary tube this one is gonna be angle 5 right yeah h is the depth right into this one for the water case it is the height right the distance in the vertical axis right yeah let's move to the next one yeah for both cases whether it's water or mercury the unknown quantity is h right the height here and if you would like to determine or calculate or to find this height you may use this formula okay the scientist has discovered this relation it depends on the surface tension okay if that fluid has a strong surface tension this effect will be prominent okay this effect will be easily noticeable okay we would be easily noticeable to this effect okay when we have strong surface tension okay any liquid that has high amount of surface tension we would be easily able to notice this effect okay and it depends on the angle cosine too okay if the angle is very small we would be able to observe higher height here distance here right the level difference here okay and if that liquid is very dense okay if that liquid has large density the height here will be small okay and if we stay in any planet that has very strong gravitational acceleration for example if you live in Uranus in Neptune or in any big planet the gravitational acceleration would be sorry for that เพิ่งเห็นอีกครับthe gravitational acceleration would be large and in a big planet the height that you could observe will be small too okay And one more thing, if you use the big capillary tube, the radius here, you would have less height. Okay, the height will not be big. Okay, because it inversely depends on the radius of the capillary tube. All right. Now let's apply this formula into a situation. Let's consider this example. Assume the contact angle between the water and the material of the tube is small enough. It means I don't know which one, right? But they say the angle phi here is very small, so this would be the case, right? Angle phi is close to 0, and angle phi is close to 0. They say it's small enough, so it means our angle phi tends to 0, and with this assumption, it means that cosine phi tends to what number? It should be here. It should be close to number 1, right? Number 1, and yeah, this will be only a number 1 and has no effect at all, right? Now let's let's consider the question: find the height to which water would rise in a capillary tube with radius equal to 5 times 10 to the negative 5. So R of the capillary tube, okay, from this point to this one, this is R, right? R here is R is 5 times 10 raised to negative 5 meter, right? It's very, very tiny, right? R is there, and assume that we stay on Earth, right? So the gravitational on Earth is 9.8, right? Let's summarize that. They say they consider water, right? So we have to use gamma water. When they don't say any temperature, it means that we have to pick up the value at the room temperature, which is 20 degrees, right? Surface tension of water at the room temperature 20 degrees Celsius is 0.073 Newton per meter, right? And the next one, rho. So rho of water, the density of water, what is that? It is in the SI system, right? It's 1 ton, right? 1,000 kilogram. ถ้าคุณตักน้ำมา1ลูกบาศก์เมตรนะครับกว้าง1เมตรสูง1เมตรยาว1เมตรนะครับมันจะต้องหนักเท่านี้นะครับ It's 1,000 kilogram or 1 ton per cubic meter. And what else? Gravitational on Earth, okay, G on Earth is 9.8, or you may also use 10, right? Meter per second square, right? The acceleration unit. What else? The radius is already there, right? Which is 5 times 10 to the negative 5 meter. So now it's time to substitute everything. They want to know h, right? What is that? So h from that formula is h from this formula is computed by equation 33, right? Which is 2 gamma by rho g r and cosine angle phi, but in this case phi would be 0, right? And it brings cosine phi to number 1, so this one is only number 1, right? And yeah, it's 2 times gamma. Gamma is gamma water is 0.073 and divided by rho, which is 1000, and G is 9.8, and R is the radius, right? R is the radius, which is 5 here, right? 5 times 10 is negative 5. Okay, and that's it. If you put it into the calculator or by using your hand, okay, you would see that you will end up with the height of 0.298, okay, 98 meter. All right, and that's the unit of the height you can observe from this capillary tube in this figure. Okay, so what is that? It is approximately 30 right, 30 centimeter, right? Yeah, 30 centimeter, 29.8 centimeter, which is approximately 1 foot, right? The length of a ruler is somehow is, right? So the height you can observe is around 1 foot. Okay, yeah. Now we arrive at different next topic, which is surface tension. Surface tension has been considered before, right? And now we arrive at the second term, which is viscosity. Viscosity is the following. Let's get into the meaning of viscosity. If the extent, the amount or the quantity to which fluids yield to shearing forces and hence flow easily and quickly depends on a quantity called the viscosity. Viscosity is like the friction at different layers of fluid. Okay, even you see a single piece of fluid, but there are different layers of fluid, and among different layers of liquid there are friction forces, okay, or it's called shearing forces, and that shearing forces will cause the viscosity. Okay, if you still cannot imagine that, let's take a look at this figure. You have here water inside a glass, and another one you have honey. Okay, both are fluid, right? And for the water case, if you try to pour the water into the jar or a cup or container like that, you will see that it's quite easy for you to let the water get into the jar, right? It's not difficult. But for the honey case, yeah, the honey can get into the jar, but you have to wait a little bit to let the honey completely flow into the jar, right? Get into the jar. And with this experiment, it means that the honey has more viscosity than the water, right? And yeah, it means that honey has more friction in different layers of its liquid. Okay, it's considerably easier to pour water out of the container than to pour honey. This is because the honey has a higher viscosity than the water. Here. ผมขออนุญาตเข้าห้องน้ำแป๊บนึงนะครับดื่มน้ำเยอะนะครับ Okay. Yeah, you have seen how the viscosity is, right? Yeah. In general sense, viscosity refers to the internal friction of the fluid. Okay, there is friction inside that fluid. Okay, and before we go to the idea, the realistic case of the fluid, we would first talk about the ideal fluid. Okay, ideal fluid is the fluid that is incompressible. Okay, it means it has a constant density. What is the reason why they say constant density? Because if you take a look at this, rho is m by v, right? Incompressible, the word in compressible means cannot, right? Cannot be compressed. Okay, it cannot be compressed. It means that the volume is constant. Okay, is constant, remains the same. When the volume is the same and the mass of that fluid, okay, let's say we consider that fluid in a closed system, the mass of that fluid doesn't disappear. Okay, there is no leak of fluid at all, so the mass will be the same. When the mass is the same, volume is the same, we will get the same value for the density. They say has a constant density. Okay, and that's the reason. And it has no internal friction or viscosity. Okay, ideal fluid has no density change, has no viscosity, but realistic, you can see, for example, honey, it has viscosity, right? Water has also viscosity. Okay, and yeah. And one more thing for the ideal fluid, it just flow without any internal friction at all. Okay, for example, take a look at this is the pipe. Okay, and you let the water, oh no, not water, an ideal fluid. Okay, I don't know what material, but it's ideal fluid. It's a kind of fluid that is ideal. Okay, it's not in reality. They flow without any friction at all, and there is no friction between that fluid to the wall inside the pipe. There is no friction among several layers of that fluid, so everywhere can move freely with the same speed because there is no friction. So if you measure the speed or the velocity at different point of this liquid, you would find the same value for the velocity or the speed. Okay, when you have the speed at the same as the same value for different point, we call non-viscous flow velocity profile. Okay, it's the velocity is the same everywhere. Okay, but it's not the case in reality. Okay, now let's consider the reality viscous flow velocity profile. In this case, the fluid is in reality. Okay, it's realistic. When the fluid flows, there is a friction between liquid and the metal inside. Okay, it's called internal friction. And among several layers of fluid, there is a friction, but it's not so strong as the friction between that fluid to the internal wall of that pipe. Okay, so there is high friction here, there is low friction here. With the low friction, the fluid can move easily. Okay, so the easy movement means the high speed or high velocity of the fluid flow here. Okay, because it's far from the friction point between internal wall of this pipe and the fluid, right? It has at the center we have less friction, so that's why we have highest amount of velocity or speed here. Okay, and the velocity profile is gonna be something like small, and large, and maximum at the center and small at the border. Okay, and yeah, now let's make everything qualitatively, right? Try to compute or see what is the effect of velocity profile and internal friction and viscosity and so on, right? As a scientist, what time is it? I should let you go at 15:40, right? We still have 25 minutes. Okay. An experiment to observe this is the following. You have oh no. How to delete this page? I'm not sure. Oh no. ไม่เป็นไรครับหน้านี้ก็ได้ Okay. Yeah. In the first stage, first situation, you have a wall like this. It's like the gummy, right? You have something like that, and you stick it to both a plane. This is a plane, okay, but we look at it from the side view. Okay, this is the plane. Okay, but we look at plane number 1, plane number 2. Okay, and here is fluid. Okay, fluid, and it's sticked to both plane, okay, in the upper surface and lower surface, right? That's the first stage. In the distance here is d, and the area at touching point is at the touching point, at the contact is a, okay, and the shape at the beginning is the shape is point A, B, C, and D, right? At the beginning we have a square A, B, C, and D. All right. And after that, someone try to pull this, okay, to the right hand side. They pull with the force F, okay, they exert the force to this plane, okay, and yeah, this is the fluid that try to be stick to this plane, right? Now let's consider the second situation. The second situation is the following. No. Yeah, the lower surface stay the same, right? And you now move the upper plane to this location, and right now it's gonna be like this. Okay, the fluid has changed its shape like this. Okay, the shape of that fluid now has been changed. It's parallel pipe. Okay, it's parallel type of square, right? This is rectangle, and now the position of each point is now it is changed. Okay, it changes from ABCD to now AD, and this one is EF. Okay, the square now has 4 corners as A, E, F, D, like this. All right, but the area still remain the same. Okay, the contact area is still the same, A, and the distance is still the same. Okay, distance D, and we would like to know what is the effect of F, okay, how F depends on, okay, F depends on what, okay, what does F depend on? What do you think? F would depend on what? We need more force for the more viscous liquid, right? F should depend on F should depend on the first relation you would be able to observe is F depend on the area A, okay? If you have greater contact area A, you need to exert more F, okay? And if you want to move it with high speed, okay, with if you want to move it very quickly with velocity V, okay, if you move it gradually with very low speed, okay, you require only small F. But if you want to move it very quickly with the speed V, you need to also increase the F. So the second factor is that F depends also on V, okay, and depends on the velocity. If you move it quickly, you need more F, okay, to do that. And the next thing is that F depends also on F depends also on the type of that liquid, which is viscosity, okay? F depends on viscosity, and no, sorry for that. There are only 3 relations, okay? The third one is F would depends on the distance, okay? If you have a less gap, okay, you need also to have more F, right? If the fluid if these two places stay very close to each other, you need more F, okay? And when D is up, D is greater, it means that you need to when D is down, right, when the gap is small, when D is down, it means that your F should be larger, right? So it means F inversely depends on the distance, all right? And with these three observation, 3 proportionality, the scientist has found that F is equal to K times A and V and divided by D. And K is a constant, right? It's a constant from the proportionality, right? From the proportionality. And K here is known to us as viscosity, okay, and it's known in variable eta. Oh, sorry for that. ตกจอพอดีนะครับ okay, and เขียนใหม่ก็ได้ครับ and the constant is known as viscosity. Okay, it's a constant, okay, and the variable they use is eta, right? It's eta, and with the long tail here. All right, that's the viscosity. Now let's get to this is what I have already explained. Okay, let's take a look at this viscosity in reality. We have several materials. For example, water at room temperature, water at the boiling temperature, 100 degrees Celsius. and whole blood, right? The blood inside our human body, and glycerin, right? And 10 WT motor oil. You know that inside the engine, we need the lubrication, right? Otherwise, we are gonna have friction, and friction will bring you to wear, right? When the engine is worn, we cannot use the engine at all. So motor oil is the substance that try to keep the to protect the engine from wear, right? Yeah, those are 4 or 5 examples of fluids that we could find in reality. So what is the meaning? Any fluid that has high value of viscosity, it means that that fluid would move difficultly, okay, with the flow rate and so on. Okay, for example, water at the room temperature is 1/1000, right? 10⁻³ Newton second per square meter, and water at the room temperature is only 1/3, right? 0.3 10⁻³ So what is the reason behind it? What is the reason why the same water has lower viscosity at higher temperature? ทำไมถึงมีอุณหภูมิทำไมอุณหภูมิสูงของเหลวไม่ใช่แค่เฉพาะน้ำครับทำไมของเหลวทำไมเนี่ยมี viscosity ต่ำลงเพราะอะไรเลยระหว่างที่ผมรอคำตอบคุณเดี๋ยวผมแคปเจอร์หน้าจอส่งให้ Alright, what is the reason behind that? ทำไมนะครับทำไมของเหลวถึงมีค่า viscosity ต่ำเมื่ออุณหภูมิสูงขึ้นครับ What's the reason? มีใครตอบได้ครับพิมพ์ตอบมาก็ได้ครับWhat is the reason? ทำไมครับอุณหภูมิสูงขึ้นแล้วของเหลวมีค่าความหนืดน้อยลงมีใครตอบได้ไหมครับ And since one right? This one too. Okay. If none of you would deliver the answer, I would say because the heat you get, you leave it inside the molecule of that liquid will a little bit break down, okay, reduce the attractive force inside that molecule. So when there is less attractive force inside that substance, the viscosity is gonna be lower, okay, because there is lower friction, right? And one thing we could observe from this table is the whole blood. Okay, the whole blood here, the blood has higher viscosity than the water. Okay, and viscosity of the blood is quite sensitive, right, to our human condition, right? If the blood cannot flow well, your body may have a problem in order to keep your body in an appropriate temperature, right? For example, if you go to some countries that has very low temperature in the winter, if your blood flow rate is not good, your body may get trouble, okay? And the blood flow rate depends directly on viscosity. And glycerine, right? Glycerine is the kind of fluid that has extremely high viscosity. Okay, the motor oil has also a large amount of the viscosity. Okay, and now let's take a look at one example. An axle of a few centimeter diameter rotates in the bearing with 1 millimeter gap. Okay, the gap here. Okay, the gap here is D. Okay, D is 1 millimeter. Okay, and it's filled with SCI33206 oil that has eta of 200 millipascal second. What is millipascal second? Well, you know that 1 pascal is equal to 1 Newton per Newton per square meter, right? You know that 1 pascal is equal to 1 Newton per square meter. So in this case, the viscosity unit could be also written as Pascal times second, right? So the unit of viscosity could be also written as Pascal times second, but what they have provided here is millipascal second, right? Millipascal second is 1 by 1000, right? 1 by 1000 millipascal. And the linear speed of this one, right? It's rotate, it goes with velocity 1 meter per second, right? Okay, that's the information from this problem. Let's solve this problem. Okay, let's solve this problem. Yeah, we have to apply this formula, right? FAV eta by D, right? We're gonna need that formula. F equal AV eta by D, right? FAV eta by D. And what is A? A is the area. They say the area here. The area is no. Yeah. If the total cylindrical area is 100 square centimeter, so the area is 100 square centimeter, right? And it's equal to 100 times 10 negative 4, right? Square meter, right? And what else? Determine the force needed to overcome the viscous friction. So what is F in this scenario, right? Anyway, we have to know everything, right? Velocity is 1 meter per second. Viscosity is here 200 millipascal second. So it's actually 200 times 10 minutes to negative 3 Pascal times second, right? And what else? FAV D is the gap, right? The gap distance here is 1 millimeter, so it's 10 less negative 3 millimeter, like that. All right, so we will substitute everything into that formula. F is equal to A, which is this one, right? It's 10 less negative 2, right? And V is velocity 1 meter per second, and eta is 0.2, right? You divide it by the distance d, which is 10 less negative 3, right? 1 millimeter, right? 1 millimeter is 10 less negative 3 meter, right? So if you move this one up, right, to the upper place, to the numerator position, you're gonna have number 10 times 0.2 is number 2, right? So it's 2 Newton, okay? If you leave the 2 Newton to this one, you can start to rotate this bearing, this axle, all right, to overcome the friction, right? So now let's get to more detail of the relation among several factors, right? If you have the pressure here at the beginning, pressure 1 and pressure 2, and you want to find the flow rate, okay? The flow rate. What is flow rate? It means the delta V by delta T, okay? The volume per time, okay? Volume per time that flows through this pipe. And of course, the velocity profile, you have high velocity at the center, lower velocity when it's far from the center, and very, very low at the border between pipe and fluid. And let's say there is the radius. This is made of cylindrical pipe, right? There is the radius from the center of the pipe to the wall of that internal pipe, right? The internal wall of the pipe. And that is V velocity. Let's say V is the mean or the average velocity of the whole fluid. And this person, Boissier, okay, Boissier is a French scientist, has found the relation between several factors in this setup, right? Depends on, of course, if you have more radius, you have bigger pipe, the flow rate is good, okay, the flow rate increases. If you have bigger pressure difference, okay, the pressure difference is high, the flow rate is going to be also high. And if you have a long distance of pipe, the flow rate will not be good because there is all the time friction, right? The water or the fluid cannot flow well if you have a long, very long pipe. And if the fluid has high viscosity, the flow rate is not also be good, okay? The flow rate is not gonna be good if your fluid is very, very viscous, okay? The viscosity of that fluid is very high, you would have low flow rate for that. And this person is known Boissier, okay, who has discovered this relation. Let's take a look at this example. We have a patient receives the blood transfusion. Okay, he needs to change his blood in the whole body by plugging the needle into his skin. And the needle has a radius of 0.2 millimeter. The length is 2 centimeters. So the needle is somehow like this. Okay, it's a kind of cylinder, and radius R is 0.2 millimeter, and the length here is 2 centimeter. All right, 2 centimeter, and the density of the blood is 1050 kilogram per cubic meter. The bottle supplied blood is 0.5 meter above the patient's arm. What is the rate of flow through the needle? So let's draw the whole mechanism, right? The whole experimental setup here. Okay, you have a container like this, and you leave the blood inside this container, and you connect it through to the pipe. Okay, to the pipe, and here is the needle. The needle is somehow this. Okay, the needle is right here, and you plug it into the human body. Okay, this is human body, and this comes somehow like this, right? I may not draw very well, right? This guy, and the height here is 0.5 meter. Okay, 0.5 meter, and the raw, this is raw blood, right? Raw density of the blood is 1050 kilogram per cubic meter, and the needle is of the length 2 centimeter, right? And the radius here, radius is which is 0.2 millimeter. Okay, radius of the needle. Okay, and what else? That's it. Okay, and one thing we need to know is the viscosity of the blood. Okay, let's get back to the table, and we would see that the viscosity, the blood has viscosity at the normal body temperature. Okay, 37 is not at room temperature 20 degrees Celsius. Okay, because our internal temperature of the body is 37 degrees Celsius, right? It's 2.7. So eta of blood is 2.7 times 10 to the negative 3 Pascal times second, right? Pascal times second. And what they want to know is delta V. Oh, sorry, it's not velocity. It's capital V by delta T. What is that, right? We need to consult Boursier. Boursier is the person who found this expression, right? Delta V depends on pi r with the power of 4 and delta pressure. Okay, and it eta L, right? L is this one, right? The length here. This is L equal to centimeter, right? And R, the radius, right? The radius is denoted by capital R, right? And what else? P1 and P2. Here we have pressure P1, okay? And here we have pressure P2. So what do you think then what is the relationship between P1 and P2? We know that the fluid flow from this one to this location. It means P1 is greater than P2, right? Okay, P1 is greater than P2. And yes, the pressure P1 and P2, the relationship between P1 and P2 is the following. P1 equals P2 plus rho GH, okay? Rho is the density of that fluid, G is the gravitational acceleration on Earth, H is the height here, okay? So it means P1 minus P2 is equal to rho GH, right? So we will substitute that into the Boltzmann formula. Delta V by delta T will be pi R with the power of 4, and P1 minus P2 is going to be rho GH, right? Rho G and H divided by 8 eta L, 8 eta L, right? And pi is pi, right? It's nothing. And R, the radius in this case is 0.2, right? Which is 0.2 times 10 to the negative 3 with the power of 4. Okay, please note that power of 4. And rho is the density of the blood, 1050 kilogram per cubic meter. G acceleration on Earth, it's 9.8, or you can simply use number 10. H is the height, which is here 0.5 meter. Okay, it's 0.5 meter, and you divide it by 8. Okay, 8 is number 8, and you have eta, which is 2.7 times 10 to the negative 3, and L is the length of the needle, right, which is 2 centimeter, right? But we have to express it in the SI scale, which is 2 times 10 to the negative 2 meter, right? So you leave it into the calculator, and you're gonna get the flow rate like very tiny, right? 0.5986 times 10 to the negative 6 cubic meter per second. Okay, and actually 7 here. Okay, 7, and that's it for this problem. Okay, now you have seen the way how to apply the Boltzmann formula, right? The flow rate of the liquid when they flow through a pipe. Okay, depends on the radius, the pressure difference, the viscosity of that fluid, and the length of the pipe too. Okay, now it's time. The time is over. We have to leave this lecture right now. So see you on Friday. If you have any question, just let me know. Okay, if not, then bye bye ครับ สวัสดีครับว่าลินทอนโอเคโอเค okay, we're gonna quit this.อ๋อเพราะอนุภาคห่างกันมากขึ้นเมื่อมีส่วนกันอ๋อโอเค we're gonna end the stream here, right? Yeah, the Zoom meeting has finished. Waiting for Lutson. We're gonna end the stream here. And we're gonna end the stream here too. And take a look at this YouTube studio, right? Yes, YouTube. No, it's impossible, and then we have to quit the stream by using this one.